All right. Okay, Chemistry 102. So we're starting off tonight with heterocyclic amines. So the whole chapter, chapter 15, deals with amines and amides. So it's chemistry that involves nitrogen, right? We're talking about organic compounds that contain nitrogen. And you can guess that a heterocyclic compound or a heterocyclic amine is some kind of cyclic compound that has at least one nitrogen in the ring. And the reason that heterocyclic amines are so important is that many are physiologically active. Many are found in biochemistry. If you've studied the structure of DNA and RNA, you're definitely used to seeing what we call the nitrogenous bases, which are heterocyclic amines. Also, I would put in here, physiologically active, I would put in here drugs, okay? Many drugs possess heterocyclic amines. In fact, if you Google most prescription drugs, you think like, oh, I've taken a prescription drug or an antibiotic or something, many of them are going to have heterocycles that have nitrogen in them. So these are some of the more common heterocycles that are monocyclic. You don't have to have any of these memorized except for pyridine. You need to know the structure of pyridine. So if you take a benzene, right, everybody in the class knows what benzene is, right? This is benzene. And all you do is replace one of the carbons with a nitrogen and you've got pyridine. So again, you have to know the structure of pyridine and to be able to recognize it. If you put two nitrogens in a ring, as is shown here like this, then you get a compound called pyrimidine. If you have a 5-membered ring with one nitrogen, it's called pyrrole, and if you have two, it's called imidazole. Again, you don't have to have those memorized, but it's nice to see them because they are ubiquitous in the chemistry of drugs, and they're also ubiquitous in biochemistry. And we're going to look at a lot of biochemistry, especially in the last third of this course. Here's some other examples. When I worked in industry, I worked for a long time on HIV drugs, and a lot of those HIV drugs were based around this heterocycle right here, which is called indole. And it's kind of as if you have a pyrrole ring attached to a benzene, right? It kind of looks like the two of them are glued together, and you get this molecule called indole. So indole is very commonly found in drugs. Over here we have purine, and this guy down here is called a porphyrin or a porphyrin ring, where you have these 4 nitrogens, and then we have these dashed lines going to M+. Well, what those dashed lines are, it's not a covalent bond and it's not an ionic bond. It's something that we call a coordination complex. It's beyond the scope of our class. But what you need to understand is that the lone pairs on the nitrogen atoms are able to retain or hold a metal cation in the center here. And if you've ever seen the structure of hemoglobin, you would know that it's an iron cation that is held inside a porphyrin ring. So that's how the metal is able to be transported around the human body. All right, so again, the porphyrin ring found in hemoglobin and myoglobin. And I promise you that when we study proteins, we're going to take a look at the structure of both hemoglobin and myoglobin. All right. Anyhow, next slide says heterocyclic amines alkaloid examples. If you've wondered what an alkaloid is just a naturally occurring compound containing nitrogen. So you see all kinds of really interesting compounds here. If you take a look at this one here, this is LSD, lysergic acid diethylamide. And you can see that not only do we have a heterocycle here, right? Here we have an indole in the molecule. Okay, we have 3 nitrogens. If you look at the structure of cocaine, it has a benzene ring in it. It also has this really interesting bicyclic structure here that has a nitrogen in the molecule. Now, that's the free base of cocaine. Of course, the free base of cocaine is crack cocaine, and the cocaine that people ingest through their olfactory, through their nose, would be the hydrochloride salt, but that's something else. The structure of nicotine. Look at nicotine. It's got a pyridine ring right here, and then you have another ring that's called a pyrrolidine. So this is called a pyrrolidine here. So you have 2 nitrogen-containing heterocycles in nicotine. This last one, it's kind of on the edge here, but you see these three OR groups, or sorry, these two ROR groups here. We have one up here, and then we have another one down here. Well, this interesting structure, which has a bridge that goes over here, we have a nitrogen in the ring. We also have, an aromatic portion in the molecule right there. Well, depending on what those R groups are, we get some really interesting organic compounds. If the two R groups are simply hydrogens, you have morphine. If you change this one down here to a methyl group, you've got codeine. And if you change both of them to acetyl groups, so AC means that you have an acetyl group like this, okay? Then you have heroin. So if the next time somebody tells you, oh, this food is like one atom away from plastic or something crazy like that, you can say, well, codeine, which is found in cough syrup, is only, what, 2 carbons, 2 oxygens, or 3 carbons and 2 oxygens and 3 hydrogens away from being heroin. So, small changes in a molecule can have dramatic physiological effects to human beings. What else do we have down here? We have vitamin B6, excuse me. We have strychnine. So strychnine is used as a poison sometimes. It also has a really interesting bridged structure here. You got a nitrogen here and here. And what's the last one? The last one is quinine or quinine, depending on the pronunciation of it. Anyhow, all right, so some interesting alkaloids. And if you want to look them up, there's plenty more interesting alkaloids out there if you wanted to know the structure of any drugs. I promise you that if you look at any commercial on TV that advertises some kind of, pill or drug that the pharmaceutical companies are pushing, I guarantee you that 9 times out of 10, the molecules will possess some kind of heterocycle that has nitrogen in it. All right, well, let's switch over. And we spent the first 2 sections just talking about amines, and now we're going to talk about amides, okay? Sometimes people pronounce them amides. I worked with a British guy who called them amides, so it doesn't matter what you call it, as long as you understand that the structure is that we have a carbonyl, and then we have a nitrogen, and then that nitrogen can have 2 R groups attached to it. Now, what the R groups are can depend on the amide, and we'll talk about that in a second. Where do we get an amide? It says that amides are formed in a reaction between a carboxylic acid derivative and an amine. So if we take a carboxylic acid, right here we just have a run-of-the-mill carboxylic acid, and we react it with an amine or ammonia derivative. Let's say we have, some kind of primary amine. Well, what we can form from that is we can form an amide, can't we, right? Where we have something like this, okay? And we're going to look at that reaction in more detail. Again, the amide bond, or an amide bond, what we call an amide bond, is the bond between the carbonyl group and the amino group. So the amide bond, and you're going to hear me use the word amide bond a lot when we get into the chapter where we talk about proteins, which is chapter 18. But the amide bond is this bond here. Okay, so the amide bond, again, I'm repeating myself, is the bond between the carbon and the nitrogen. The single bond that is called the amide bond. Okay, and there are many ways to make amides, but again, we're going to take a look at that in a second. All right, let's talk about the physical properties of amides. It says here that most amides are, in fact, solids at room temperature due to internal hydrogen bonding. Also, they're not bases. Okay, when we talked about amines, right, we said that amines are bases, okay? Amides are not bases. And there's a reason why an amide is not a base. Let me show you why an amine is a base first. If I draw a primary amine, for example, okay, right? The lone pair of electrons that's on the nitrogen is totally just sitting there, and it's available to accept a proton, right? A base is a proton acceptor. So this pair of electrons that I have in the black circle is completely available. And so that explains why an amine is a base, because they can donate electrons, right? Another definition of an acid is an electron acceptor, and another definition of a base is an electron donor. But if we look at, and I'm going to move this out of the way because I don't want to confuse you, so I'll move this over here. Amines are bases, cool. But if we look at the resonance structure of an amide, it explains why they are not bases. Let me show you. If we draw the Lewis structure of an amide, we have two bonds, two lone pairs in our oxygen. We have our nitrogen here. The nitrogen has a lone pair, and let's say it's got two R groups, and we'll call them R prime and R double prime. Well, the reason that an amide is not a base is because this pair of electrons is not available. And you might be thinking, well, come on, this just looks like it's just sitting there to me, Mr. Dion. Well, hold the phone. It's because they participate in something called resonance, okay? Which means that the electrons are not in that one place. They're not what we call localized. They're in fact delocalized. So not only can the amide exist as I have it drawn already, but we can also draw or represent the amide like this, where we have three lone pairs on the oxygen, which would give it a negative charge. We have a double bond to this carbon, and now we have four bonds to our nitrogen and no lone pair. And so now it's got a positive charge. Now it's important that you understand that resonance doesn't mean that it's vibrating back and forth and back and forth. No, it's not doing that. What these two structures are saying is that neither of them is a perfectly accurate description of the amide, right? Normally we draw an amide like this, but when we draw the resonance structure, this one over here, it helps us to understand why this lone pair of electrons is not available. It's because it's delocalized, right? The electrons are not located on that nitrogen, okay? The structure is going to be a hybrid of these two resonance structures. The way you could think about a resonance structure is something like a nectarine, okay? A nectarine is what you get when you cross a plum and a peach. If you look at a nectarine, it's not, you don't look at it 1 second, it's a plum, and then look at it a few minutes later, and now it's a peach. No, it's always a nectarine. But you can think about it as being the hybrid of those two. And so that's what these resonance structures are representing. Anyhow, again, all you really need to know for this class is that amides are not bases, and it's because the lone pair on the nitrogen is participating in what we call resonance, which renders it unable to accept a proton. All right, let's talk about the hydrogen bonding in amides. Here we have a figure over here that shows amide bonding between, or hydrogen bonding between amides. And how would they hydrogen bond? Well, there's many different opportunities for hydrogen bonding between amides, right? Again, if we draw the generic structure of an amide right here, we have lone pairs on the oxygen, which are delta minus. Why? Because oxygen is more electronegative than carbon. We also have the lone pair on the nitrogen, and we'll draw two hydrogens on here like this. And then we can say that these hydrogens are delta plus. Why? Because nitrogen is more electronegative than the hydrogen atoms. And so if we draw the lone pairs in on, let's say, this oxygen here, we could draw another hydrogen bond, right, like this, okay? All right, we could draw another hydrogen bond like this. Okay, anyhow, so the hydrogen bonds are going to be between the nitrogen-hydrogen bonds of one amide and the carbonyl of another. And this is what gives amides very high boiling points, okay? This is why most of them have such high boiling points that they're solids at room temperature. Some simple amides, ones that are small, are going to be soluble in water, but just like amines or alcohols, as the size of the R groups increases, their solubility is going to decrease. Let's talk about how we name an amide, okay? Before we name an amide, I want to classify what a primary, secondary, and tertiary amide are. And I don't have a lot of space for this, so I'll do it right here. Now, remember that the generic structure of an amide was something like this, okay? Well, let's just call it, we'll call this R2, something like this. Well, there's three possibilities. If we have our carbonyl and we have our nitrogen attached to two hydrogens like this, we call this a primary amide. If you have your R group, your carbonyl, and your nitrogen has one hydrogen and one R group, we call this a secondary amide. And if your amide has R groups attached to everything, right, you've got an R group here and an R group here, then it's called a tertiary amide. Okay, so you need to know the difference between a primary amide when you have two hydrogens, a secondary amide when you have one, and then a tertiary when you have no hydrogens attached to your nitrogen of your amide. Okay, so primary, secondary, and tertiary amide. For example, this amide that I have drawn here is a primary amide. All right. Well, when it comes to naming amides, we need to learn how to name primary, secondary, and tertiary amides. Here's how we do it. The names are going to be derived from the carboxylic acid. Okay, we remove oic acid and we replace with amide. That's for IUPAC nomenclature. So we'll put here, we'll put IUPAC. Okay. If it's a common name, if we're using the common name of a carboxylic acid, we remove ic acid and we replace with amide. All right. If you have a nitrogen substituent, and this only happens for secondary and tertiary amides, then you prefix the substituent with an N that's italicized, and then you give the name of the substituent. Now, you might be like, what are you talking about, Mr. Dan? Well, I promise you that once you see it, it's going to be become abundantly clear. Take a look at this amide right here. If we had this as a carboxylic acid, right? If we had, instead of a primary amide, let's say we had our OH group here. This would be called ethanoic acid, right? So we remove the oic acid and we replace it with amide, and it becomes ethanamide. What's the common name of that carboxylic acid? It's acetic acid. So we remove ic acid and it becomes acetamide, which I normally pronounce as acetamide. Okay? Same thing over here. If you had a 3-carbon carboxylic acid, and I probably don't even need to draw it for you, you probably know them better than I do by now. We have propanoic acid, would be, again, the top ones would be the IUPAC names. Okay? And then propanoic acid becomes propane amide. And the common name would be propionic acid. We remove the ic, and it becomes propion amide. Okay? So again, these ones here are both primary amides. When you get down to both of these, which are both secondary amides, since we have a methyl group, just one methyl group, we call it N-methyl propanamide, right? Because we've got 3 carbons in the parent. That's the IUPAC name. The common name would be, and it's not listed here, it would be N-methyl propionamide. Right? Same thing here. We have N-propyl hexanamide. And since we didn't look at a common name for a 6-carbon carboxylic acid, this is the only name that we would use. It would be N-propyl hexanamide. All right, give me a thumbs up if you follow me on, even part of the way, on the nomenclature of amides. Definitely takes a little bit of practice, but when we learned how to name secondary and tertiary amines, you remember that we did the prefixing with the letter N, and then we would list the name of the alkyl group, N-ethyl, N-isopropyl, so on and so forth. All right, great. That's awesome. Well, let's take a look at the names of some simple amides. The first 1, 2, 3, 4. These are the first 4 primary amides, right? If they were all carboxylic acids, you'd go from methanoic acid, ethanoic acid. What am I doing wrong here? Well, the first one's just generic. Sorry, my bad. My mistake. Okay. So we have 1, 2, 3. There we go. So the first one would be methanoic acid, ethanoic acid, propanoic acid. So we have methanamide, ethanamide, propanamide. What would their common names be? The common names would be formic acid, acetic acid, propionic acid. So we have formamide, acetamide, and propionamide. And then they just kind of help you out with some secondary amides down here. We have N-methyl methanamide, which would be N-methyl Formamide would be the common name, and then we have N-methyl ethanamide, which would be N-methyl acetamide. Okay, so again, it's crucial that you memorize the names of the first of the simple amides, right? The common names and the IUPAC names. You know how to come up with those. Let me just show you one more thing that's not really covered on here, but you can, and you probably would guess this trying to practice problems. But let's say we had this, okay? Let's say we had this as our amide. This is a tertiary amide. You might be wondering, well, how do I name a tertiary amide? Since we have two carbons, it would be ethanamide, and we have two methyl groups, so you would call this NN dimethyl ethanamide. Okay, and then the common name would be NN dimethyl acetamide. Okay, like that. And again, what's the best way to master it? Watch me do it. Well, that'll help you a little bit, but the best way to do it is to try it yourself. Okay, nomenclature is best done alone. You know, you learn the rules, then you practice them and practice them until you know they kind of become old hat. Anyhow, let's talk about how you would make an amide. I remember the first job that I ever had was working as a medicinal chemist in 2001. I was really young, you know, super excited to start this job. And I was talking to another guy who had some experience. And, you know, we were talking about just making drugs and, you know, what kind of targets we were looking at. I was working on an antidepressant at the time, and this guy was working on a diabetes medication at the time. And he was talking about making a lot of amides. He said, you know, I'm making a lot of amides these days. And he said, oh, come on now. How many ways are there to make an amide? And what he meant by it was, there's a million ways to do it. And I was thinking, oh, yeah, sure. I was so young, I only knew a few ways, but there are many, 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 many ways to make amides. In fact, if you're interested in a chemistry money-making opportunity, if any of you are like, ooh, money, you piqued my interest, Mr. Dion. Well, if you can develop a new reagent that will help chemists to make amide bonds, you'll always be able to sell it. People are always looking for new ways to make amide bonds, and there are lots of good ones, lots of great reagents out here. Okay, this is one of the most classic ways to make an amide, and the reason that it's taught so heavily in introductory organic chemistry classes, what you see down here, is because not only is it a good way to make an amide, and I would say good, not great. It also gets your students to think about acid-base chemistry. So let's take a look. It says primary and secondary amines can react with an acid chloride or an anhydride to produce an amide. But what's interesting, and this is something that we don't see a whole heck of a lot of in this class, is that you need 2 molar equivalents of the amine, the nitrogen source, compared to your acid chloride or your acid anhydride. Think about most of the reactions that we look at. They have, you know, most things that we look at is 1 plus 1 gives you, you know, 1 mole, right? 1 mole of an alcohol plus 1 mole of carboxylic acid will give you 1 mole of ester. Well, not when you make an amide from an amine and an acid chloride or an acid anhydride. Check this out. Very different. We have 1 mole of acid chloride, but we need double the amount of our amine. Now, why the heck would that be? Well, there's a very good reason for it. Okay, and there's not a lot of space here, but I want to explain it to you. Okay, for the people who are really interested in this kind of stuff, there's a good reason why you need 2 equivalents of ammonia. Now, this is a little bit beyond the scope of our course, but I know you're going to follow me here. Okay, what happens is the first molecule of ammonia is going to form a bond between the lone pair on the nitrogen and this carbon right here, okay? But remember, this carbon already has 4 bonds. Carbon cannot have more than 4 bonds. So what happens is it collides with the carbon at such a force that it forces the chlorine off of the molecule. And so what you end up with is something that looks like this. Let me draw it out for you so you follow me here. You've got the carbon, you still have the oxygen, but now you've got a nitrogen that has 1, 2, 3 hydrogens attached to it. When nitrogen has 4 bonds, it's got a positive charge. Now we've got this, and we've also got the chloride that's somewhere floating around in the solution, right? Because we knocked it out. Okay, so what happens is You don't want to isolate a salt. You're trying to make a beautiful amide. And so what you have to do is you have to use 2 moles of the amine. Why? Because the second one, I'll draw the second one here, okay, is going to act as a base, and it's going to pull one of these protons off so that you end up with the beautiful amide, and then the NH3 plus an H plus a proton gives you ammonium, and then you've got your chloride. Give me a thumbs up if you follow me on that rationale. Why you need 2 molecules of the amine. Cha? All right, thanks, Gavin. I really appreciate that. Okay. Now, again, for this class, if you want to just memorize it, like, yes, Mr. Dion, I know I need to have 2 equivalents of the amine. That's all great. There's nothing wrong with that at all. It's just that seeing the reaction happen, right? This is actually how it occurs, can clear things up for some students. Okay, we call this a reaction mechanism. If any of you decide to take organic chemistry over an entire year, so that would be organic chemistry for people who want to be in dental school or medical school or pharmacy school, or want to complete a biology degree or a chemistry degree, something like that, you would look at many mechanisms in detail over the course of an entire year of organic chemistry. Just one more thing I want to say about this, and this is kind of a funny thing, but think about this. Okay, if you had to do a reaction between this acid chloride and your amine, but you need 2 molecules, that means you need double the amount of the amine in terms of moles, but you have 2 moles of the amine and you only end up with 1 mole of the product. Okay, so that means that half of your amine is just going in the garbage, right? It's going in here, and you're not going to use that at all. So literally, the one thing that I've always hated about this reaction, and you ask most chemists, and they'll say it's kind of a shaking your fist at the sky kind of thing, is that the reaction is great in that you can make an amide, no problem. But let's say the amine is something that you can't buy, it's something that you have to make and you work really hard for it, to make a few milligrams or grams of it. Well, when you do the reaction, half of it just goes in the trash, right? Half of it ends up in a waste, which is always a bit of a heartbreaker. Anyhow, here are some examples of amides that people would make using this kind of chemistry. Or here's one example right here. Let's say we had butanoyl chloride, right? We talked about how to name acid chlorides in the carboxylic acid chapter. Again, if you were to treat that with methanamine, you have to have 2 molecules of methanamine, right? The first one is the one that is attached to the carbonyl, but then you need a second molecule of the amine to behave as a base and take off that proton to make this methylammonium chloride salt. Okay, now instead of using a chlorine here, or instead of using an acid chloride, we can use an acid anhydride, and it does the exact same thing. If you didn't follow me the first time, let me show you again. The first molecule of your base is going to walla walla bing bang, hit the carbon so hard, and it's going to knock all of this part off. What would you end up with? You would end up with this. You'd have R, C, double bond O. You'd have a nitrogen with 1, 2, 3 hydrogens attached to it. And then what about all this? You would have oxygen with a negative charge, a carbon, and then an R group. And so what's going to happen is this carboxylate is going to pull off a proton like this. Then you're going to end up with the amide. And what did I do wrong here? Oh, sorry, my mistake. So the carboxylate is not going to pull that off. A second molecule of ammonia, right? The second molecule of the base is going to come in and it's going to pull off this proton here like that, so that you end up with a carboxylic acid salt. All right. Again, the way that our book teaches it is just to memorize it, but it's always nice to see how things work. Well, where would you find amides? Well, all through your body, for one thing. All the proteins and enzymes in your body are filled with amide bond after amide bond after amide bond. But here's some examples of places you would find an amide bond. If you've ever heard of aspartame, people vilify aspartame, and it depends on the person. Some people are really afraid of aspartame. It's a sweetener in things like sugar-free gum or Diet Coke or Coke Zero or something like that. Well, aspartame is nothing more than an amide bond between two amino acids that are found in your body. Okay, these are naturally occurring amino acids. What else? We have neotame over here. So neotame is also an artificial sweetener that's made from a modified aspartic acid, which is also a naturally occurring amino acid, and phenylalanine is just a methyl ester of phenylalanine. So again, these artificial sweeteners are made from naturally occurring amino acids, and they're just linked together by amide bonds. All right. What was I going to say about these? Yeah, the problem with things like aspartame is one of the reasons why you can't use aspartame for cooking is because if you try to make muffins with aspartame in them, the amide bond will break when it's heated up, and so it will not taste sweet. It'll taste disgusting. All right. Anyhow, what about blowing an amide apart? If you think about, go back to the carboxylic acid chapter. Remember we learned esterification? When you combine a carboxylic acid and an alcohol and acid, and you heat it up and you remove water, you form an ester. Then what did we talk about the next day? We talked about hydrolyzing an ester. Well, you can do the same thing here. You're going to hydrolyze an amide, and just like we talked about the hydrolysis of an ester in acid or base, well, we can hydrolyze an amide in acid or base. Depending on which environment you hydrolyze an amide in, if you do it in acid or in base, you end up with different products, okay? If you're in acid, you're going to end up with a carboxylic acid. Makes sense, right? You should have an acid in an acid environment. But instead of isolating an amine, right? That's what I meant to do. Instead of isolating an amine, you're not going to do that because when you have an amine in acid, it's going to take a proton to become an ammonium ion, right? Because what? Amines are bases. If you have a base plus an acid, it's going to accept the proton from the acid. Conversely, if you take an amide and you hydrolyze it in base, instead of ending up with a carboxylic acid, you're going to end up with a carboxylic acid salt and an amine. Why would you end up with an amine instead of an alkyl ammonium? Because an amine is a base and you're in a base. Okay? Why would I end up with a carboxylic acid salt? Because you can't end up with a carboxylic acid in a base, right? The base is going to rip off the proton here. It's going to remove that proton so that you end up with a carboxylate or a carboxylic acid salt. Now again, what is the bond that's broken during amide hydrolysis? The amide bond. Remember I taught you this several slides ago. I said if you look at the structure of an amide, the bond between the carbon and the nitrogen, this bond right here, that is the amide bond. That's the one that was formed on this slide here, right? You were forming an amide bond. You formed an amide bond here. And when we do the hydrolysis of an amide, that's the bond that gets broken. This bond here, this bond here, the amide bond. Give me a thumbs up if you follow me on hydrolysis of an amide bond. And a little bit of acid-base chemistry that goes along with it. Shah, is anybody there with me? All right, great. Yeah, you have to understand that amines are bases. So if you put an amine in an acid, acids and bases are going to react together. If you have an amine in a basic environment, bases and bases aren't going to react together. If conversely, if you have a carboxylic acid and it's in an acid environment, it's not going to react. It's just going to be a carboxylic acid. But if you have a carboxylic acid in a basic environment, it's going to make a carboxylate, right? The base is going to do a deprotonation. Acid-base chemistry is not always intuitive to students, but it's very important that you have some understanding of acid-base chemistry. It's a topic that's very difficult to memorize your way through, okay? A little bit of understanding will give you a much better grade than trying to memorize what's going to happen in every acid-base scenario. All right, section 15.4 is really a preview of chapter 18, because in chapter 18 we deal with proteins, and amino acids. So this is chapter 18. So that's what this is a preview of: amino acids, proteins, and protein synthesis. If you've ever wondered what the heck is an amino acid, Mr. Dion, well, if you think about the name amino acid, it suggests that you would have an amine and an acid in the same compound, right? Well, let me show you what the generic structure of an amino acid looks like. There we go. The generic structure of an amino acid looks something like this. You have an acid, which has a carbon attached to it, and it also has an amine on the exact same carbon, okay? So amino acid, right? That's where the name amino acid comes from. Now, this carbon here we call the alpha carbon, and so most of the amino acids that we're going to be concerned with in this class are what are called alpha amino acids. There are other types of amino acids, but generally speaking in this class we'll deal with the alpha amino acids. So if you're the kind of person that's heard about proteins, right, back when the Atkins diet or the South Beach diet was very popular, human beings were very obsessed with consuming large amounts of protein. And if you've ever wondered, like, what is a protein really, Mr. Dion? A protein is nothing more than a polymer. You mean like a polymer like plastic or like Kevlar or nylon, right? Or what else? Garbage bags, polyethylene terephthalate? In a way, yeah. Plastics and Kevlar, right? Bulletproof vests, those are synthetic polymers. Those are polymers that were invented by human beings, right? By men and women. However, proteins are polymers that are made up of amino acids. And so a protein is nothing more than a naturally occurring polymer, right? Made up of amino acids that are found in a living organism. So what happens is we take a bunch of these amino acids and we link them together, kind of like paper dolls, okay? Now, the way that it's drawn here compared to the way I've drawn it here may not be completely intuitive. So let me redraw the alpha amino acid for you down here in a way that might make more sense, okay? Let me see here. There's not a lot of room here, but if I draw my alpha amino acid like this, okay, so I've got an R group down here, and then I've got my NH2 here, and then I've got a hydrogen up here like this. So this is just me redrawing this molecule right here. So if you take a bunch of these, and let me see if I can do some copy paste magic here for you. So if I move this up here, and then I copy it and paste it, and there's not a lot of room, okay? If you add these two together, okay, what you're going to end up with is what's called a peptide, okay? A peptide is just a really small protein. How would you take these two compounds and make this compound here? Let me show you. What you would do is you would remove H2O. You'd remove one hydrogen from here, a hydrogen from here, and this oxygen. And then you'd have what? You'd have the nitrogen with only one hydrogen. And there is your amide bond, which we also call a peptide bond. So a peptide bond and an amide bond need the exact same thing. So protein powder just contains nothing more than a lot of protein molecules in it. That's all it is, Sadie. So when you consume protein powder, all you're drinking is long strands of amino acids linked together. Nothing fancier than that. Okay, that's all it is. All right. Except instead of having two amino acids, you've got hundreds or maybe thousands of amino acids all linked together. Now, I want to address one more thing about this structure of this peptide. You probably noticed that you're like, well, over here it says NH3+, and here you have a negative charge, and you don't have either in your amino acids, Mr. Dion. What's your problem? Well, let me show you. If you think about the amino acid that I have drawn up here, you've got an amine, which is a base, and you've got a carboxylic acid, which is an acid, in the same molecule. So it makes sense that this proton is going to disappear, and where is it going to show up? Right? It's going to show up on the nitrogen because the nitrogen is basic, so it's going to accept the proton, and the carboxylic acid is acidic. It's going to donate the proton. So in fact, amino acids generally speaking, at physiological pH, a lot of them exist like this, where they have both a negative and positive charge in the same molecule. We call that a Zwita ion, which means two ions in the same molecule. Anyhow, I'm not going to ask you anything about transfer RNA on the next course, or sorry, on the next exam. So I'm going to skip this slide right here. Again, here's the generic structure of an amino acid. I do want you to know this generic structure of an amino acid for your next exam. Again, here's the generic structure that I just drew, okay? And if you don't believe me, what you see down here is the same thing as this. If you draw this, okay, and you put NH3 plus over here, and you have an R group down here, these two are the exact same thing. All right, and we call these alpha amino acids because this is our alpha carbon, and it's got an amino group attached to it, like that. Now, if you think about all the people in our class, for example, okay, or all the people in your family, and you look at their DNA, and you look at the similarities in DNA between human beings, right? You probably know that human beings have a lot of similarities between our DNA and that of a cucumber, okay? But the similarities in DNA between people is even much greater, right? We have a lot, human beings have a lot more in common in our DNA than we do different in our DNA. But, you know, without sounding corny, and this is just a way that I found to describe it, and students tend to understand. If you think about all the people in our class, right? We all have two arms, two eyes, you know, two legs, you know, blah, blah, blah. We have a lot of similarities, but what makes us unique, right? What makes us all unique? You could say maybe our personality, for example, okay? Our personality is something that makes us unique. Well, what makes amino acids, the naturally occurring amino acids that you would find in something like protein powder or tuna, okay, what makes them all unique is the R group, okay? This part here is going to remain almost all the time. It's going to remain constant, not 100% of the time, but most of the time. So what makes the different amino acids different is the R group, okay? For example, if the R group is just a hydrogen, okay, so when that R group is equal to a hydrogen, that's the simplest possible amino acid, and that is called glycine, okay? If the R group is a methyl group, that's called alanine, okay? If the R group is, and you don't have to have these memorized, if the R is CH2 with a benzene ring dangling off it like that, okay, then it's called phenylalanine. And I could go on, but I don't want to bore you with all these right now. I just want you to have an idea of what differentiates the amino acids. All right.